Assalamualaikum warahmatullahi wabarakatuh. Today I want present about matrix and their application. In our group is Muhammad Aiman, Muhammad Nazmi, Muhammad Aikal and Muhammad Ridwan.
What is matrix? Matrices are rectangular arrays of numbers, symbols, or expressions arranged in rows and columns. Matrix basics. Definition: a matrix is a rectangular arrangement of numbers in rows and columns, written inside brackets. Notation: A equals AMN, where AMN is the element in the M, the row, and N the column. Example: A equals 2, 3, 4, 5. Types of matrices: row matrix, column matrix, square matrix, zero matrix, identity matrix, diagonal matrix. Row matrix 372, order 1 by 3. 1 row, 3 columns, column matrix. A equals 372, order 3 by 1. 3 rows, 1 column.
Square matrix. A equals 2, 5, 7, 3, 1, 4, 6, 8, 9. Order 3 by 3, 3 rows, 3 column. A square matrix has the same number of rows and columns. Rectangular matrix. A equals 1, 4, 6, 8, 2, 5, 7, 9. Order 2 by 4, 2 rows, 4 column. A rectangular matrix has different numbers of rows and columns. Identity matrix. I equals 100010001. An identity matrix is a square matrix where all the diagonal elements are 1, and all other elements are 0. It is denoted as I and plays a special role in matrix operations, similar to the number 1 in multiplication. Inverse matrix. A equals ABCD. The inverse of a 2 times 2 matrix is found using the formula: A inverse equals 1 divide det A multiply D negative B negative CA. The det A equals A multiply D minus B multiply C. Identity matrix 3 by 3. Inverse of a 3 by 3 matrix. Example: let's see how 3 by 3 matrix looks. M equals ABCDEFGHI. Consider the given 3 by 3 matrix. A equals 1, 2, 3, 0, 1, 4, 5, 6, 0. Let's see what are the steps to find inverse. First step: check the given matrix is invertible. Example: det A equals 1 multiply 0 minus 24 minus 2 multiply 0 minus 20 plus 3 multiply 0 minus 5. The last answer of det A is 1. Then, finding the determinant of the 2 by 2 minor matrices. Step 2. Now, we have to find the determinants of each and every 2 by 2 minor matrices for first row elements. 1, 4, 6, 0 equals negative 24. 0, 4, 5, 0 equals negative 20. 0, 1, 5, 6 equals negative 5 for second row element. 2, 3, 6, 0 equals negative 18. 1, 3, 5, 0 equals negative 15. 1, 2, 5, 6 equals negative 4 for third row element. 2, 3, 1, 4 equals 5. 1, 3, 0, 4 equals 4. 1, 2, 0, 1 equals 1. Now, the new matrix formed is A equals negative 24 negative 20 negative 5 negative 18 negative 15 negative 4 5 4 1. Then, formulating the matrix of cofactors. Step 3. Now, to create the adjoint or the adjugated matrix, reverse the sign of the alternating terms as shown below. The obtained matrix is A equals negative 24 negative 20 negative 5 negative 18 negative 15 negative 4 5 4 1. Multiply plus minus plus minus plus minus plus minus plus. Answer is negative 24 20 negative 5 18 negative 1 5 4 5 negative 4 1. Then, take the transpose of the cofactor matrix to get the adjugate matrix. Step 4. Now take the transpose of the obtained cofactor matrix. Thus, adjugate A equals negative 2 4 1 8 5 2 0 negative 15 negative 4 negative 5 4 1. Lastly, find the inverse of 3 by 3 matrix. By using formula, A inverse equals 1 divide determinant A multiply adjugate A. Thus, the inverse of the given matrix is A inverse equals 1 divide 1 multiply negative 2 4 1 8 5 2 0 negative 15 negative 4 negative 5 4 1. Operation of matrices. Adding matrices is as simple as adding numbers, but there's one important rule. The matrices must have the same order, i.e., the same number of rows and columns. Once this condition is met, the addition is performed by adding corresponding elements of both matrices to form a new matrix. Addition of matrices. A equals A11 A12 A21 A22, B equals A11 A12 A21 A22, A plus B equals A11 plus B11 A12 plus B12 A21 plus B21 A22 plus B22. Operation of matrices. Subtraction of matrices. To subtract two matrices, the matrices must have the same order, i.e., the same number of rows and columns. Subtraction is performed by subtracting the corresponding elements of the second matrix from the first matrix to form a new matrix. This completes the subtraction operation. A equals A11 A12 A21 A22, B equals B11 B12 B21 B22, AB equals A11 B11 A12 B12 A21 B21 A22 B22. Scalar multiplication. Scalar multiplication of matrices. For any matrix A equals Aij, m times n, if we multiply the matrix A with any scalar, say k, then the scalar is multiplied by each element of the matrix, and this is called the scalar multiplication of matrices. A equals A11 A12 A21 A22, Ka equals K times A11 K times A12 K times A21 K times A22. Operation of matrices. Transpose operation of a matrix. The transpose operation of a matrix rearranges its rows into columns and its columns into rows. For a matrix A of order m times n, denoted as A equals Aij, m times n, its transpose is represented by it and is defined as A equals ABCDEF, order 2 times 3. A transpose equals ADBECF, order 3 times 2. Operation of matrices. Matrix multiplication is the operation that helps us to multiply two matrices. This is different from algebraic multiplication, and not all the matrices can be multiplied. Only those matrices can be multiplied where the number of columns in the first is equal to the number of rows in the second, i.e. for matrix M times n and matrix Bn times P. The multiplication is possible for any other matrices where the column of the first matrix is not equal to the row in the second matrix. The multiplication is not possible. ABCD times IJKL equals A times I plus B times KA times J plus B times LC times I plus D times KC times plus D times L. Operation of matrices. Inverse operation of a matrix. The inverse of a matrix A exists only if A is a square matrix, i.e., has the same number of rows and columns, and its determinant is non-zero. A equals ABCD, A inverse equals ABCD, inverse equals 1 over A times D, B times C, DBCA. Examples of real-life applications of matrices. Computer graphics. Matrices control image transformations such as rotation, scaling, translation, and 3D rendering. For example, when a 3D object in a video game rotates or moves, a transformation matrix updates the object's coordinates on the screen. Electrical circuits. Matrices simplify solving complex circuit equations using Kirchhoff's laws. Engineers can represent the system of equations as a matrix and solve for unknown voltages or currents efficiently.
Okay, this is the question, real life application question. A factory manufactures three types of sound cards for personal computers, namely A, B, and C. All cards consist of three different components as given below. Type A, 1 transistor, 2 resistors, and 3 capacitors. Type B, 2 transistors, 4 resistors, and 5 capacitors. And type C, 3 transistors, 5 resistors, and 6 capacitors. The number of sound cards produced per day for type A, type B, and type C is 26, 46, and 57 respectively. Show the above information in form of metric question. The first step is we rewrite like step. We write at the step 1 the matrix 1, 2, 3, 2, 4, 5, and 3, 4, 3, 5, 6, and the transistor, resistor, capacitors is equal to 26, 46, and 57. Question B is by using Cramer's rule, find the number of transistor, resistor, and capacitor used per day of type A, type B, and type C. Step 1 is rewrite, and step 2 is find the determinant that A, and we get the answer is -1. And step 3 is find the determinant for the transistor, and determinant for the transistor is -2. And step 4 is we find the determinant of resistor, and we will get the determinant is -3. And last is we find the determinant for capacitor, and the determinant for capacitor is -6. And we will use the formula this is to find the determinant for transistor is the determinant transistor divide by the determinant. We will get the determinant for transistor is 2, and resistor 3, and capacitor is 6. Question C is by using metric inversion method, find the number of transistor, resistor, and capacitor used per day for type A, B, and C. Step 1 is rewrite A multiplied by X is equals to B. And step 2 is find the determinant, and we will get the determinant is -1. Step 3 is find minor. Minor is in column 1, and row 1 is we will get, and we use AD, A multiplied by D, and minus B multiplied by C, and we will get -1. In minor column 1 and row 2 same, we will get -3. Minor 1, 3, we will get -2. And minor 1, 2 in row 2 column 1 we will get -3. In row 2 column 2 we will get -3, and column 2 and row 3 we will get -1. In row 3 column 1 we will get -2, and column 2 we will get -1, column 3 we will get 0. And the metric is right like this, metric M. Next step is step 4 is we use a cofactor M, plus minus plus, minus plus minus, and plus minus plus. We will get the matrix is -1, 3, -2, 3, -3, 1, -2, 1, 0. Step 5 is transpose the metric. We will get the metric is -1, 3, -2, 3, -3, 1, -2, 1, 0. Step 6 is we inverse the metric of A to A -1. The formula is 1 per determinant A multiplied by adjustment A. And we will get the matrix is 1, -3, 2, -3, 3, -1, 2, -1, and 0. Step 7 is find the value of T, R, and C. The formula is X is equals to A multiplied by B. And after we multiply all the element, we will get same like Cramer's rule. The answer is transistor 2, resistors 3, and capacitors is 6. Question D is compare the two methods and state which one you think is better. Give a simple justification. The easy method to use is Cramer's rule. Cramer's rule is easier because it has clear and systematic calculation steps where each variable can be determined directly using the formula. This method does not require finding the inverse matrix a negative one, which is more complicated and time consuming. In addition, for a small system such as 3 multiplied by 3 matrix, Cramer's rule is faster, simpler, and easier to understand compared to the inverse matrix method. Therefore, Cramer's rule is the easier and more suitable method to solve the system of linear equations.
Conclusion. In summary, matrices provides a powerful mathematical tool for organizing, analyzing, and solving complex problems efficiently. Throughout this chapter, we explored the concepts of matrix operations, determinants, inverses, and their real-world applications. Mastering these concepts enhances logical thinking and problem-solving skills, which are essential in various fields such as engineering and physics. Ultimately, matrices serve as a fundamental bridge between abstract mathematics and practical applications, reinforcing the importance of precision and analytical reasoning in modern technology and scientific advancement. That's all from we. Thank you for watching.